let's consider a weight on an incline. Here we have a skier on a slope, and her mass includes her equipment, and it's 60 kilograms. The skier's on the slope, and we want to know what's her acceleration if we can neglect friction, and then what's her acceleration if we have some friction. So let's start by drawing a free body diagram. You can kind of see one here. Let's go ahead and draw our own. This is a 25-degree slope, so let's go ahead and label some things we know. We know our mass is 60 kilograms, and we know our slope angle is 25 degrees. Now let's draw our free body diagram. So we'll include the skier. First, let's have some coordinate axes. On slopes, it can frequently be useful to rotate our coordinate axes to align with the slope. So that's what I've done here. I've included a rotated coordinate axis, so my x is aligned with the slope. We'll now have the forces acting on the skier. We've got weight acting downward. We've got our normal force acting normal to the surface. So this is in the y direction. We've got friction acting along the slope in the negative, well, opposing motion here. That's my positive x direction, just with how I've defined my x. And then we'll include some relevant dimensional information. So this is on a 25-degree slope. We can use some geometry here to say that this then would be a 25-degree angle in here by alternate interior angles. You can also find that with triangles and finding this angle in here and then using complementary angles to get this 25 degrees, however you want to do it. And then we'll note that because this is a 90-degree angle here, that normal force, remember, is always normal to the surface. We can now find the angle here that this makes with the horizontal, if we care about that, 65 degrees. We can now use the fact that if I want to get this angle to the vertical here, I can get that as 25 degrees. And we can get really any angles we want in here using some geometry like that. Some relevant angles might be if we want to put it in terms of, instead of straight up and down, if we want to put it in terms of our actual rotated coordinate system, we can get the angle that this weight makes with respect to the y-axis and with respect to the x-axis. And so we'll do that here. We'll use this triangle to do the sums of these angles, have to sum to 180. You've got a right triangle in there. So you have 65 degrees is the angle that it makes with the x-axis, and 25 degrees is the angle that my weight makes with the y-axis. That lets us project those or resolve that weight onto the x and the y axes as these components wx and wy. All right, we've done our free body diagram with some geometry there. We're now going to apply Newton's law, Newton's laws, specifically the second law, to be able to hopefully find the acceleration that we're trying to find. So this second law says the sums of the forces are equal to mass times acceleration. Let's consider the x component and say that that means that if I look at the x components, I should be able to do this. So my x components, remember, are on this diagonal here. What we have is we have some component of the weight, and it's the x component of the weight. So that is acting in the downward, and then friction is opposing that. Here I've called my x positive going up to the right, but when I wrote this here, I've basically just, anyway, this is what it is. These are the components, and then we'll include the negative in the next step here because it's going in the negative direction. So my x component of my weight is negative w cosine 65 degrees. And why cosine? Well, because 65 degrees is the angle that's between my weight and my x-axis, so cosine projects it onto that axis. The friction here for part A is negligible, so we're saying that that disappears. Now we've got our expression, and we want to solve this for the acceleration. So let's see if we can do that. My weight, I have to think about what my weight's equal to, and I think my weight should just equal mass times gravity, right? That's what weight is. So I have mass. I can now substitute in mass times gravity, and now I should be able to solve this. We notice that the masses cancel here. We can divide both sides by mass. Those cancel out. And now we have my acceleration is just whatever's left over here, g times cosine of 65, which evaluated becomes negative 4.14 meters per second squared in the i-hat direction. The negative means that we're acting in the negative direction. If I had defined my x as positive going down the slope, then this would have been a positive, right? This negative or positive depends on my choice of coordinates. So my acceleration, since I'm not coming up and down off the surface, I don't even need to consider the y component. I can say my acceleration should be that magnitude in a direction that's 25 degrees below the horizontal. Either one of these is fine, whichever one makes most sense to you. If I wanted to consider the y components, though, we could, and we'll call up, my y direction positive there. We can plug those in and say, this is my normal force plus whatever the y component of my weight is. The y component of my weight should be a negative, and it's going to be that mass times gravity times either cosine of 25 degrees or sine of 65 degrees. So here it's normal force minus mass times gravity of sine of 65 degrees is equal to mass times acceleration, and as long as we're staying on the slope, that acceleration is 0. So this lets us solve for the normal force in terms of the stuff we know, mass times gravity. That wasn't part of the problem, but it's a thing we can do, and if you need that, we now have the normal force. What about part B? What about the acceleration if the friction is 45 newtons? Well, we can reuse all of this work up until the point where we said friction was 0. So coming back here, we can say, well, this is all true. It's just now we have a positive friction force that goes in there. And so we plug in the positive friction force, and I'll leave it for you, if you want, to solve through for what the acceleration is now. You have all the information over here. You now divide by the mass, and now the mass matters because it doesn't cancel out. That friction force doesn't have a mass term in it with how we've written it here. So you divide by the mass, and you should be able to find that acceleration. And hopefully, since the friction is slowing down our motion, you would find that that acceleration will be less than what it was without friction.